Our journey begins with an orange, 24 centuries ago. Can we cut this orange in half, then in halves again, then again ad infinitum? In 400 BCE, a Greek philosopher, Democritus, had already a very precise idea. After millions of divisions, there's only a tiny particle left, a tiny particle which can't be cut anymore, and this is how Democritus chose to name it, the indivisible, which in Greek is the atom. The atom is so small that it's invisible, but this minuscule atom, gathered together with millions, billions of other atoms, forms matter, like sand forms a beach. At the beginning of the 3rd century BCE, another Greek philosopher, Epicurus, suggested the following. We know the beach is made of grains of sand, even if it seems smooth and uniform from afar. So maybe we can consider that matter, like the beach, is also granular. The rock doesn't become a tiny pebble instantaneously. The river erodes the stone grain by grain by separating tiny atoms, but atoms themselves aren't worn down. This is the theory of the Latin poet Lucretius. But his long poem, one of the few vestiges of the ancient Greek atomic theory, sank into oblivion for 15 centuries. During the Middle Ages, the notion of the atom is forgotten. But in 1417, the ancient poem of Lucretius is discovered again. This revived the atomic theory which captivated every scholar of the period. Etienne de Clave, the most virulent of them, maintains that if atoms are invisible, they are not imperceptible. If salt dissolves in water, it doesn't disappear. We can taste it, even if we can't see it anymore. A self-consuming candle, does that mean transformation or disappearance of matter? The 18th century brings the period of experimentation, when observation is no longer enough. Mercury turns red when a candle burns under a cloche, but its weight remains exactly the same. Nothing is lost, nothing is created, everything is transformed, say Lavoisier and Dalton, the chemists proposing this experiment. Matter is conserved, and yet matter has changed. Perhaps matter is actually made of small particles, of atoms, whose number remains the same, yet combine in new ways to create different things. Observing the pollen of a rare flower floating in a drop of water, the botanist Robert Brown, at the beginning of the 19th century, saw the pollen wiggle in a strange way. This frenetic motion, later measured by Jean Perrin and modelled by Einstein, was the atom dance. It's the dance of the water molecules banging into the grains of pollen. Thus, atoms are in perpetual motion. They deflect the light pollen when they hit it, but objects bigger than pollen are hit by so many atoms because of their size that the motion of atoms is cancelled out. However, the basis of this reasoning was not quite true. After 23 centuries of careful reflection, one experiment was enough to overturn atomic theory. Electricity passing through a gas can create, in specific conditions, a beam of green light, a cathode ray. But this ray is always the same, no matter which gas is used. Joseph Thomson, the physicist who did this experiment at the end of the 19th century, deduced that the ray was made of particles torn from the gas atoms. But if we can tear these particles, these electrons, from atoms, it means the atom can be divided. It isn't the little marble we thought of for centuries. Instead of a marble, Thomson proposed the image of a plum pudding, in which plums are the electrons. What we have been calling atom for such a long time isn't an atom anymore. It is not indivisible. A very thin sheet of gold leaf is formed of just a few layers of atoms. In the 20th century, the physicist Ernest Rutherford tried bombarding this gold leaf with positive particles. Much to his surprise, most of the particles went through the gold leaf easily. suggesting that atoms are mostly made of empty space. But some particles bounced back and appeared to be deflected by a very dense but very small mass. Very small because only very few particles bounced back. So the atom isn't solid, but it's composed of a tiny core, a lot of emptiness, and some electrons spinning round the core. The atom's core is positive, the atom's electrons are negative, and positive and negative charges attract each other. But then how can electrons rotate around the core without crushing into it? Here the solution is not provided by an experiment, but by a theory, the quantum theory, and specifically an equation established by the physicist Erwin Schrödinger. Atoms don't collapse because electrons are not little marbles, electrons act like waves. Or rather, as if the electron enveloped the core like a cloud, and each electron is a cloud that overlays the previous one. But an electron is no more a cloud than a marble. The electron is everywhere around the atom without having a solid body, without allowing us to give it a fixed position. Here ends the field where seeing and experimenting are enough to understand. With Schrödinger begins an abstract way of thinking, with new rules, in order to grasp the complexity of matter. We can draw an approximate image of those rules, but not test them with our senses. This is how we've attempted for 24 centuries, and most likely for many centuries to come, to understand what is around us and within us. This is a quest, an infinite quest, to grasp what is the most fundamental. If, in some cataclysm, all of scientific knowledge were to be destroyed, says Richard Feynman, if all of scientific knowledge were to be destroyed and only one sentence was passed on to the next generation of creatures, what statement would contain the most information in the fewest words? I believe it's the atomic hypothesis that all things are made of atoms, little particles that move around in perpetual motion, attracting each other when they're a little distance apart, but repelling when squeezed into one another. In that one sentence you will see there is an enormous amount of information about the world, if just a little information and thinking are applied.